positive terms. Obviously, we're not going to consider negatives today, right? So all we're worried about is positive series. What is a positive series? So we have some series, right? If it's positive, if all the terms are positive, what's happening to the series? Right? So we would have the partial sums. Each term is bigger than the next, right? I mean, if you write that in English, each partial sum, I should say. So if I take S sub 3, it's smaller than S sub 4. So that's what we're referring to. And then all of the terms are greater than 0, so that's what happens. So all of them are positive. Obviously, it's added one part. Right? Okay. There are two things that can happen with a positive series. It's a little theorem in your book. It's called the dichotomy of positive series. There are two things that can happen. Here are my term. Partial sums. Okay, I can have a series that what's this series doing? Converge or diverge? Yeah, this one. So we have a series that can diverge, right? That's one option. The numbers just add up to infinity, right? How can we have a series that converges without decreasing? You got to think the difference here between sequences and series. They have it has to be increasing because it's a positive series.
Well, does it have to be positive x's or does it have to be positive y's?
Okay, so the term numbers are 1, 2, 3, 4. Those are pretty much set, right? Okay.
So I'm thinking
If it's positive y values or positive partial sums, what's going to happen? If you have a positive number added to a positive number, does it increase? Okay.
I'm thinking if it's negative y, does it still increase?
It can't be negative. We're only working with positives.
Yeah, I understand that. But I was just
Oh, you mean
like in the negative y values, that would be positive x, and it would still be increasing.
So it would still be doing this
Still going
though.
up to 0. Yeah.
Right. You're thinking, again, I'm going to tell you, are you talking about a sequence or a series? Remember, sequence terms must converge to 0, which I think is what you're thinking, or a series to converge, right? How would a series converge? The terms have to get smaller and smaller, right? What's that called? What's that called in series? In series talk. It's not an asymptote, that's function talk.
It's to converge to a number.
What? Bound, an upper bound. But some has to have an upper bound. Okay. So words. Okay, if there is an upper bound to the series, it converges. Remember, what are the terms here though? What are happening to the sequence of terms? They are converting to 0, right? The terms are going to zero, the partial sums are converging to some number. It's not cheap. It's very expensive. It's a lot of the price. I have to tell you. Do you know the difference, though? You see the difference between the sequence terms versus the series adding those terms. Right? So I could have something like 1 half, 1 fourth, 1 eighth. Right? These terms go to zero, right? But if I add them up, that's a sequence series. If I add them up, this actually converges to some number. We'll actually look at this. It's called a p series. This is 1 over n squared, right? Okay, so we have to have an upper bound. That's key. Right? We're going to give you something called the integral test. Okay? So we have the nth term test, right? And we have the now we'll have the integral test. Then we'll get the comparison test while the limit compares. We have we're gonna have like 8 or 10 tests. So this is one of them. Remember, you have to meet the conditions. Okay. And this one's really nice because it's based on what you already know. So we use an integral to calculate convergence. Okay. So we let a sub n equal to f of n, where f of x, that's not what I wanted to write. Come on, brain. I know you're under a tremendous amount of pressure right now. Please work. Is positive decreasing and continuous. For x greater than or equal to 1. Notice the conditions, right? We have to meet those conditions. So we basically turn the series into a function. We determine, is it positive, is it decreasing, and is it continuous? Then we can apply the integral test. Okay. Here's the first. If the integral from 1 to infinity, what's that integral from? Indefinite integrals. We're using indefinite integrals here, right? Converges, then the series converges. And what do I mean by the integral converges? It gives an answer. Right, we get a number. I'll show you one. Okay, here's the second one. If the integral diverges, what do you think happens to the series? This is a predictable one. These do not prove themselves. You can't. That is a complete mathematical no-no. Saying, proving, using yourself to prove yourself. This is saying if the integral converges, then the series converges. Those are really pretty perfect. So what about something like this? So let's make sure we have a function that matches it, right? Is the function always positive for 1 to infinity, right? So our interval will always match our series limits, right? So is this positive for all positive x values? Yeah, it is, right? Okay, is it decreasing? This is not something you have to really show. Okay, what's the first one? 1/2 more. Okay, it's decreasing, right? And is it continuous? Where is this not continuous? 0, but is that in our domain? Nope. So we're good, right? We've met all of these conditions up here. Yeah? Okay, so we can use the integral from 1 to infinity of 1 over x dx to determine convergence or divergence. Right? You can do that. Go. Oh wait, hold on. That's not right. Don't watch me. Let's just start working right here. Yeah. Write that in place. Now we can move on. That's what you guys have already done. So what you got? So what happens to the series now? Yep. So since integral from 1 to infinity of f of x dx diverges, so does series. Does series from n equals 1 to infinity more complicated, huh? Alright, so we got a function. Our interval is 1 to infinity. It's positive. Yeah, it has to be. that's when you can just say, yeah, if you plug in, you're gonna get a positive. The only time you'll ever run into the possibility this not happening, of course, is when there are negatives or subtractions. Okay, is it decreasing? How do you know? Right, the bottom is always bigger than the top. Okay, good reasoning. The book actually goes through the derivative, right, showing the derivative is negative. So if you did that, it's kind of an ugly quotient rule, right? So you get 1 minus 3x squared over, this is, I didn't, that's the quotient rule, summary of it. The bottom is always positive, right? The top, any positive x I plug in, is it going to be negative? So we're always going to get a negative, and that's where that minus sign comes. So it's decreasing, right? And continuous. Yeah, check. You gotta check for this condition every time. So well, that sounds fantastic. All right. Improper integral with what method are we going to use to solve it? Substitution. Yep. Come on, arm, slow down a little bit. Oh, 1/2. Right? We can leave it in terms of u, but we have to change our limits, right? So if u is, or if this is 1, u is 2, and it's still going to be infinity. Not a big change, but we want to do that. So what's the integral there? Negative 1 over 2u. So you the negative 2, add 1 to get negative 1, divide by negative 1, that should be right. That is going to give us 4. So since series is something of the form one over n to the p. P can be any number. What could it be? 1 to the n? 1 over n to the n? Could. But for our purposes, p is going to be a solid number. Like 2. So p would be a real number. This series converges for what p-values do you think? What's the value of p here? 1, right? Did it diverge or converge? It diverged. Okay, so we know p is out of the running, or 1 is out of the running. So do you think it's greater than 1 or less than 1? Yeah. Anything else happens, it diverges. So very straightforward. It's called the p-series test. That kind of showed you one already. The proof of this is here's an example of a p-series. Tell me if it converges or diverges. Well, that's the cube root. Yeah, because the p is 1/3, right? So this diverges because p is 1/3, which is less than 1, right? I can put a dozen up there, you probably get them all right. All you have to do is look at the value of p. That's it. 1 over n squared does what? Oh, if I did this, it does not apply. Well, no, but you can look at this and see what happens. Diverges, right? But, so yeah, p-series has to be 1 over. So this one would actually converge. Be careful. Oh, go ahead. Yeah, you could say the series converges because it's a p-series with p greater than 1. That's it. Yeah. No, it's very nice. These tests are very nice. If you meet the conditions, done. Be very careful that you do not mix the p-series up with a geometric series. Okay. So this is a geometric series. This is a p-series. See where the n is different. Then we talked about the conditions for that. So we have prelim 1 through 5. And then exercises 5, 8, 10, and 11. We'll have to know that. Friday we're going to have 2 more tests. Comparison and limit comparison tests. We'll probably put some memory cards together for those.